Good evening. This is Boaz Atterberg, and the topic of our discussion this evening is analytical solution to robot kinematics. What I like to do when I start the analytical solution is to use MathCAD, have the tool ready. Also, I like to have the formulation of what is that we're calculating. We're looking for the absolute acceleration of the tool center point in this example. And I like to have also the definitions of the scalar values of all the known variables, and also the definitions of the transformation matrix. Also like to have a little sketch of the diagram so I could figure out, if needed, the directions of the variables. We have also another tool over here, which is Microsoft Paint, that I like to have it handy as needed. So the first thing I do is I come over here and I print screen of the formulation. I go over here to Paint and I cut it, go to MathCAD, and then paste it. So now I have a presentation of what I'm looking for. I can enlarge it, so I have it pretty nice size, and I can start my formulation. The first thing that I like to do is put all the variables. I can use over here there are symbols such as alpha, theta. It may be some time consuming, so it will be quicker if we just call it by some letters. So I call theta. We'll define that equals to 30. We can also use different units, but I think what I'll do the conversion just to save time, convert this to radians by multiplying times 3.14 and divided by 180, and this is what it is in radians. Then omega, I can call this omega and define this as 60 RPM. And to change that to radians per second, we need to divide that by 60. And what we need to do is divide it by 60, not multiply. So take it back, divide by 60. And then what we need to do is multiply that times 2 pi, which is 6.28 radians per revolution. So this is our omega. Last, we have G equals to 9.8 meter per second square. Okay, now what we need to do is construct the formulation over here for the unknown variables. So let's call the absolute acceleration, we call it, let's say d2 r dt2. Okay, this is the absolute acceleration, and we could define the vectors. We have here several vectors. We can add them up by going over here to matrix, and we could now put the matrix together. We have the first matrix is for A1. A1 is in the direction of x2, so it's in the x direction. So we come over here and put, A1 is in the direction of the z direction. So A1 will be 20, and this will be 0 and 0. And then we have a vector we have to add to it. Now if you want to come over here, we just have to carefully walk and add another matrix, which is a vector. And the second vector is A2. A2 is 30 in a x direction. So we put over here 30 and 0 and 0. Then we have to add to it another vector, which is alpha cos R2. So alpha is in a z direction. So we have here a vector that is in a z direction, 0, 0. I can put here alpha, or I can just simply put the value. If I put the alpha, if I put the values, then I can work with the parameters. Since I start putting the values, not the expression, then we have here 20 radians per second. And this is, we have to cross it, so we go over here to matrix algebra operation, and we have a cross, and we have another vector, which is R. R is going in the y direction. No, I'm sorry, in x direction. So R1, we're talking about R2 here is 1, 0, 0. And so this is alpha, the tangential acceleration. Now we do in the centrifugal acceleration. So we need omega, and omega is, again, we put a vector here, which is 0, 0, and omega is 60 radians per second, which is 6.28, 6.28, and we cross it by itself. So we come over here to the matrix operation, and we do a cross, and we put another omega. Let's see if we can copy it. This, no, it doesn't work. Okay, so I'll put it another time. So it's 0, 0, 6.28, and this will have to be crossed again. So another matrix operation. Of course, and then we put another vector, and this vector is going to be R2. So R2 is 1 again, 0, 0. No, R2 is in a x2 direction, so it's 1, 0, 0. Then we come over here, and we have to add the Coriolis. So, okay. So the Coriolis is 2 times, so 2 times. And we have to have here a vector, which is omega. So it's again 0, 0, 0, 0, and 6.828. And we have to cross it with the vector of V2. And V2 is in the x2 direction, 1.5 meter per second. So it's 1.5. And this is 0, 0. Finally, we have G. So G is another vector which is operating in a minus z direction, so it's minus 9.8. So when we add all of these up, we come in here, so it gives us the value of the components of this vector from here to here in the x2 coordinate system. Now you want to transform this vector from x2 coordinate system to x0 coordinate system. So we have to multiply this times the matrix. So the vector, we call this, we copy this, and we'll underscore this as the components in coordinate system 0. And now what we'll do is we generate the transformation matrix. We already know that this is a unit matrix, so it's not going to change much. And what we have here is a cosine of theta. And we need to go over here to functions, all functions. And we go over here to trigonometric functions. And what we need is sine and cosine. So we take, first of all, is a cosine. So we only need it once. So that's cosine of 0.523, 0.523. And we can copy this and put this also over here. And over here we have 1. This is 0. This is 0. This is 0. This is 0. And over here we have minus sign. So we need to come over here to the trig area, pick up the sign, and then put over here a minus sign, and 0.523 is the value of theta, and then I could copy it and paste it over here, and now I have the transformation matrix. I have to multiply that times this vector here, which we found over here. So I multiply it times this vector. So all I have to do is just copy and put here times. It has to actually be right in here. So the way to do it is to walk slowly and then times and put the number, and this is the result. These are the coordinates of the total acceleration in the x0, y0, and z0. We have 10, 27.5, and 28. So just to see what it was like when we were doing the graphical solution, let's print screen this. We can also just bring this over here, print screen it, go over here to the Paint, copy it, go back to our presentation, do over here duplicate of slide, remove this, paste it, and then we can save it. And then let's see if we bring up, so it's minus 27, 28, and 10. And if we bring up open, we bring up the graphical solution. The result was 29, 28, and 10. So we did confirm the solution, and that's basically conclude our MathCAD presentation. Thank you.